The main goal of this section of notes is for you to describe the normal states of matter and those phase transitions. Many of you learned this in 8th grade and probably before. However, I find that students still struggle with it because they don't stop and think. The thing that we're going to do here is we're going to actually add the math associated with those phase transitions as well. And in the next set of notes, we're going to talk about what are called phase diagrams. Before you started this video, you were supposed to label each state of matter and each change of state. So you have to understand what I mean when I say those particular terms or when I use those terms. What I tell students to do is to always think about what you're familiar with. If I think about ice, going to just liquid water, and then finally going to steam. And again, I'm still talking about water here. You know that in order for this process to happen, you have to add energy. And most of you can pretty much tell me that when ice turns into liquid water, that's melting. When water goes into steam, that is actually called vaporization. A lot of students want to call it boiling, and boiling is a way or a method in which that occurs, but the broad term or the big umbrella term is vaporization. And then most of you have been exposed to what's called sublimation. Sublimation is when you go directly from a solid to a gas without passing through the liquid state. The only thing I'm going to point out on this diagram for those of you that aren't familiar is deposition. Deposition is the reverse of sublimation. The second thing I asked you to do was to talk about those factors that determine a state of matter for a given pressure. Kinetic energy and intermolecular forces holding those particles together. Remember that solids typically have low kinetic energy with strong intermolecular forces. Solids and liquids are both what we call condensed states of matter. On the other side of the spectrum, we have high kinetic energy for our gases and very weak, we assume non-existent, intermolecular forces. As we go through and we talk about these different changes of state, we're going to talk about the addition or removal of energy. Remember that as I add energy, that's endothermic. So the processes with arrows going up are my endothermic processes: sublimation, vaporization, and melting. When I remove energy, that's exothermic. Or when energy is released, that's another way of thinking about it. And that's represented on this particular diagram with those down arrows. Students oftentimes really struggle with freezing. The easiest thing to do, again, is to go back and write what happens to ice, and just remember that ice to liquid to a gas, that gives me an endothermic process, and of course the reverse would be exothermic. What exactly is sublimation? Sublimation is when you go from a solid, you add a little bit of energy directly to a gas. Since I'm adding energy into my system, that's an endothermic process. Most common example, and the one we're going to see in class, is dry ice. Dry ice is really solid CO2. Most of you have seen this. They use it a lot of times in like rock concerts or on stages to create the illusion of fog. That dry ice is going to go directly from a solid to a gas without ever passing through the liquid stage. Now realize what this energy is doing. As I add energy, those particles are going to speed up until they can break those intermolecular forces holding them together. Once they break those intermolecular forces, they're free to become gases. Deposition is the reverse process. In deposition, I have a gas going directly to a solid and releasing energy in the process. Since it's releasing energy, or energy is exiting, that would be exothermic process. So what's happening on the particle level here? In this case, energy is being removed As that energy is removed, those particles are going to be slowing down such that intermolecular forces become a bigger factor and they start to kind of stick together if you want to think of them that way. Sublimation and deposition are opposite processes. So I can actually rewrite my phase change equations that I wrote as what we call equilibrium equations. Equilibrium equations are reversible reactions. And the way you read these is it depends on which way you read them. If I'm reading from left to right, I get my solid plus energy giving me a gas. If I read from the other direction, I read it as a gas, gives me a solid plus energy. So I can represent that with just one equation instead of having to keep writing multiple equations. The other thing I like to do at this point is to introduce you to what's called Le Chatelier's principle. We won't get to it in this class, but you'll definitely see it later in chemistry. And what this Le Chatelier's principle says is it says if I disrupt my equilibrium, then my system is going to adjust. And you have seen this. You already know that if I add energy, I'm going to make more gas. We say that the equilibrium shifts to the production of more gas. If I remove energy, the equilibrium is going to shift and I'm going to make more solid. Equilibrium is the rate of producing one is the same as the rate of producing the reverse. Melting. Ice being the most common example, or snow in my picture there. In the case of melting, I have a solid. I'm adding energy. And I'm producing a liquid. Since energy is going in, that's an endothermic process. So again, as I add energy, my particles speed up. They speed up to the point at which they can break those intermolecular forces. In the case of water, that would be hydrogen bonds. Remember, hydrogen bonds are my strongest intermolecular forces, so it takes a little more energy to break those apart. At the melting point, so what I have here is a heating curve. This was like what you did on web activity 10-6. So I'm going to be looking at my melting point. And when I look at my melting point, what you see is I'm continuing to add energy. That's what's on the x-axis, but temperature is constant. So while melting is occurring, while I have both solid and liquid together, temperature is going to be the same. Since temperature is the same, that means the average kinetic energy is constant. So oftentimes students look at this graph and they go, well, Ms. Betcha, this doesn't make sense. I'm adding more energy, but my temperature is not changing. Well, if I'm not changing kinetic energy, then I have to be changing potential energy. And that's what's happening with this phase change. As I add energy, that energy is being used to pull those particles apart. So the potential energy is what is actually changing here. Molar heat of fusion is the amount of energy required to melt a mole of solid. Molar heat of fusion of water is 6.02 kilojoules per mole. So that means it takes 6.02 kilojoules of energy for every 1 mole, or to melt 1 mole of ice, aka 18.02 grams. Like we did in the last unit, I can represent that in an equation. I have a couple of different choices. I can just list solid to liquid water and write the delta H, which is the heat of the reaction, is 6.02 kilojoules, since there's a 1 in front of my water. My other option would be to write H2O with a solid. This is a positive delta H, so it's an endothermic process. I could represent my energy as a reactant and then write my liquid water. The reason I have this picture here again on this slide, and I gave you one that's just a slide by itself, is because I want to show you a couple of things. The first is when I talk about this delta H, the 6.02 kilojoules, I can only use that number for that part of the curve. In the last unit, we were calculating energy absorbed or released, and whether you realized it or not, we didn't do any phase changes within a specific substance. So we were able to use Q equals MC delta T. So when I'm just talking about what's going on with the water without a phase change, I can use Q equals MC delta T. If I'm just talking about what's going on as a solid without a phase change, I can use Q equals mc delta T. However, if I go across that temperature range, if I include a phase change in my calculation or in my problem, then I have to do two different types of calculation. I have to use Q equals mc delta T for the energy in one state, and then I have to use the delta H calculation when I'm calculating the amount of energy to actually convert all of that solid into a liquid. Freezing is the opposite of melting. So in freezing, I start with a liquid and I produce a solid plus energy. This is the one that students struggle with the most, because when you think about freezing, you do not think about it as being an exothermic reaction. Exothermic process because energy is released during freezing. The example we talked about before was the fact that we spray oranges with water when there's going to be a deep freeze. And the hope is that when that water freezes, it's going to freeze before the orange. It actually produces energy, and enough energy to keep that orange from freezing itself. So what's happening here in this exothermic reaction? How am I able to actually release energy? Well, as that energy is released, those particles are slowing down, and when they slow down, they're going to go closer together. Closer particles mean lower potential energy. So that's how that process happens. Well, similar to melting point, at the freezing point, and the only thing that makes this the freezing point is the fact that this is what we call a cooling curve. It's going the other direction. We're cooling down. I know that this is the freezing point for water because I know that water typically freezes at 0 degrees Celsius. At that freezing point, again, temperature does not change. The average kinetic energy of those particles is constant, so what's actually changing is that decrease in potential energy. The other term I need to introduce here is the term normal freezing point. The key word here is whenever you see the word normal, that means at 1 atm. Water freezes at 0 degrees Celsius is not always a true statement because it depends on the atmospheric pressure. And atmospheric pressure, we learned in topic 2, varies depending upon elevation or weather patterns. Well, just like we had a molar heat of fusion, we also have a molar heat of solidification. It is all negative 6.02 kilojoules per mole. Now this time it's negative because energy is being released. This is exothermic again. And if you compare that to the molar heat of fusion, you'll see that that was a positive 6.02 because it was an endothermic process. This problem asks us to calculate the grams of ice if 505 kilojoules of energy is released. I'm freezing water, so I'm going from liquid water to solid water. And I know that that is going to give me 6.02 kilojoules. The problem asked me to figure out how many grams of ice were made if 505 kilojoules of energy was released. So I do the 505 kilojoules, put that over 1. It's negative because that energy is being released. According to my molar heat of fusion, there are negative 6.02 kilojoules, or there are 6.02 kilojoules per every 1 mole of water that freezes. That's how much energy is released. And we know that in 1 mole of water, there are 18.02 grams. So I need to plug all of that information into my calculator, and I get 1511.64 grams. Using my sig fig rules, I start it with 3 sig figs. I need to end with 3 sig figs. Melting and freezing are opposite processes, so they basically occur at the same temperature, and that's only true for crystalline solids. So just a reminder, amorphous, irregular pattern crystalline solids have a regular 3D pattern, like water. Since they are opposite processes, the energy that it takes to melt 1 mole of ice is going to be the energy that is released when 1 mole of water actually freezes. Melting is an endothermic process, so it's a positive delta H there. Freezing is an exothermic process, so that's why we have the negative there. Like we did before, we can rewrite these phase change equations. When I add energy, we know that we're going to make more liquid. That equilibrium shifts. If I take energy out of my system, my equilibrium will shift to make more solid. Condensation. Condensation is a gas giving me a liquid plus energy. Since energy is on the product side, energy is released or given off. That's an exothermic process as well. As those particles slow down, they are going to start to come together and kind of stick together. Those intermolecular forces play a bigger role. At the point of condensation, temperature doesn't change. That means the average kinetic energy of the particles is constant. It means the energy that is given off is due to the fact that those particles are coming closer together, so there's less potential energy. Molar heat of condensation is actually negative 40.7 kilojoules per mole. So I can write that. In equation form, again, since it's exothermic, I could have said plus 40.7 kilojoules like we did in the last unit. Vaporization is the opposite process. In vaporization, we have a liquid plus energy going to a gas. That's an endothermic process, energy in. So as I add energy, those particles pick up enough energy, kinetic energy, to overcome those intermolecular forces, and they're able to become gases. Happens via two mechanisms, the first of which is evaporation. Evaporation differs from boiling. Evaporation happens at the surface of a liquid, whereas boiling is going to occur throughout the liquid. And that's what this picture is trying to show you. So when I look at evaporation, I only see it happening here. Why is that? Reason is those particles at the surface of a liquid don't have as many intermolecular forces holding them in. Right? If I look at a particle way down inside this liquid, there's intermolecular forces all over the place, making and breaking all of the time. Those particles at my surface don't have those intermolecular forces surrounding it 360 degrees. So it's a lot easier for those particles to get a little bit of energy or to get enough energy to overcome intermolecular forces. Boiling, on the other hand, when I look at boiling, is happening throughout the liquid, and that's what all these little dots are supposed to represent. Molar heat of vaporization would just be the opposite sign of the molar heat of condensation. The number stays the same because they're opposite processes. So if I want to solve this problem, it asks me how much energy is needed to vaporize 75 grams of water at its boiling point. This time I'm trying to find energy. So vaporize means to go from a liquid to a gas. My delta H value is 40.7 kilojoules. Now again, because this is per mole, when I read my equation, I can just take that per mole and drop that off there. 75 grams of water goes over 1. We know that there are 18.02 grams for every 1 mole of water. And according to my delta H, it takes 40.7 kilojoules of energy for every 1 mole of water, or to convert each mole of water into a gas. When I multiply all of that out, I get an answer of 169 kilojoules. And we got to be careful. Again, we're on this part of my curve. We're at the boiling point. So since I'm on the flat part, I'm using a delta H calculation, which involves stoichiometry. Last unit, we were not getting to the boiling point. We were typically below it. So we were using Q equals MC delta T. So the molar heat of condensation is equal to the molar heat of vaporization. Vaporization is an endothermic process, so that would have a positive value. Molar heat of condensation is an exothermic process, so that's going to have a negative value. Like we did before, if I increase energy, I'm going to make more gas. According to Le Chatelier's principle, my equilibrium will shift to make more gas. And you know that the reverse is true. If I take energy away from my system, my equilibrium will shift to make more liquid. Boiling and evaporation are such important topics that we have a couple extra slides on them by themselves. Big thing here is that a liquid won't boil until its vapor pressure is equal to atmospheric pressure. The way I think about this is that you always have some kind of pressure pushing down on this liquid, and in order for that liquid to start to boil, those bubbles have to have enough pressure in and of themselves to overcome what's pushing them down. When I look at just one little bubble, realize what's happening surrounding that bubble. This would be the liquid part surrounding the bubble. And then I've managed to get a few of these particles free, giving me that one bubble. So again, in order for this liquid to really boil throughout the liquid, I have to have this happening, and this particular vapor pressure has to be equal to atmospheric pressure. The other thing I do expect you to know is that the lower that atmospheric pressure, the lower the boiling point is going to be. And the classic example here is comparing sea level with Denver. The atmospheric pressure in Mile High City is much lower, so water actually will boil at a lower temperature. In Denver, water boils at about 95 degrees Celsius. Last thing on this slide is the normal boiling point always means at 1 atmosphere. So up until this point, when I said at what temperature does water boil, most of you would have said 100 degrees Celsius. That's not always true. At the boiling point, so reading my graph, boiling point, notice that temperature does not change, which means the average kinetic energy is constant. So the question I often get is, well, Ms. Betcha, we continue to add energy. What's happening? Well, that added energy is being used to increase the distance between those particles or increase potential energy. The other thing I'm going to point out to you, because there's a question on your worksheet, notice that my heat of fusion going from a solid to a liquid and heat of vaporization going from a liquid to a vapor, the relative sizes of those two lines is very different. Last thing to talk about here is a little more about evaporation. Evaporation is a cooling process. I think we've actually talked about this a little bit, but let's just review a minute. Remember, evaporation is a surface phenomenon. Those particles at the surface don't have as many intermolecular forces holding them down, so they just gain enough energy to escape the liquid. So my analogy here is if I take 10 runners, have them go run a 5K, and then I take the top 3 runners out, well, the average speed of those runners is going to drop. They're not going to be as fast, overall average, if I take the fastest guys out. So I think that's the easiest way to think about what's going on here. My guys at the top overcome those intermolecular forces. They're the ones that are moving the fastest. When they leave, the overall average is going to be lower, which results in a cooling effect. Last slide here is just to summarize. I said it a couple of times. When I read these curves, a couple of things. I know that this curve is for water. It tells me at the top, but I can also look at my data and see that the normal melting point is 0 degrees and the normal boiling point would be 100 degrees. Whenever we have one phase and we're calculating energy changes, we use Q equals MC delta T. And that's what we did last unit. What's new in this unit is that when we're talking about phase changes, we have to use those delta H calculations, which involve stoichiometry. So tomorrow when you come in, we will do some practice on this and hopefully you'll get really good at it.